Oh, hello there. Sorry, doing a little bit of stretching here. It's going to stretch really big like this chapter. This lecture is going to be a little bit on the long side. Good to do a little bit of stretching. Stretch a little bit, stretch a little bit. More stretching. Oh, too much stretching. Hang on. Let's fix ourselves here. There we go. Are still listening to the side. This is chapter 8, part 2, where we talk about types of reactions. And it's a little bit on the long side, but it'll be okay. I should be quiet then.
Okay, welcome back here. Chapter 8, part 2 up on tap here. So in the first part of chapter 8, we talked really about chemical equations, how to write chemical equations in a sense, how to balance them. We talked about different ways to balance different types of equations. So now we're going to talk in the rest of this chapter about reactions and more specifically ways to classify reactions. As I mentioned, I think in the first part of the chapter here, there's many different ways you can classify even the same reaction, depending on sort of what you're looking for. But ultimately, when we talk about types of reactions, there's really three reasons why a reaction sort of takes place. For the most part, the three main reasons why a reaction takes place is the first one is the formation of a solid. So again, it's why a reaction takes place. Second reason is formation of our friend water, a little H2O. So the formation of water is really the second reason why a reaction takes place. And the last reason, pretty much, for why a reaction takes place is a transfer of electrons. So for the most part, you pretty much can break down all reactions to one of these three things taking place. And when we talk about reactions, there's sort of two big classifications of reactions. There are certain types of reactions which can be classified as double displacement reactions. And there's also ones that are classified as redox reactions. Redox reactions, as we'll talk about a little bit later on in this chapter, are oxidation and reduction reactions. Between these two sort of big classification of reactions, and that's sort of how you can think about it, they're sort of like two big umbrellas, and double displacement is sort of a big umbrella description of a type of reaction is taking place. And underneath that description, as we will talk about later on in this chapter, there's more specific classification of reactions that you could do. And redox is also sort of a big umbrella of types of reactions that take place. Once again, you could also get very more specific in terms of the way that you classify reactions. So, how do these two big classifications sort of match up with these three reasons why a reaction takes place? Well, our double displacement reactions, as we will talk about, pretty much take care of the first two reasons there why a reaction takes place. It takes care of the formation of a solid and also water. So basically, number one and number two up there all fall under the double displacement big umbrella. We'll talk about more specific classifications of double displacement reactions shortly, but making a solid, the formation of water, those two pretty much under that double displacement umbrella. The other reason why a reaction takes place is our transfer of electrons, and that is pretty much all about redox reactions. So redox reactions, as we will talk about, is all about transferring of electrons. And between these two big categories of reactions, it almost pretty much covers all the reasons why any reaction takes place. It really does sort of boil down to these three things. Either you made a solid, either you made water, or you have some electrons being transferred. Those are pretty much the big three in terms of reasons why a reaction takes place. So you want to kind of keep that in mind as we go through these different classifications. And we'll kind of point out as we go through them each of these things be happening, the solid being formed, water being formed, electrons being transferred. So let's take a look first off, and sort of the first type of reactions that we're going to really talk about are double displacement reactions. And in general, all double displacement reactions pretty much follow the same sort of pattern. So when you look at your reactants, you have two things there. And they're not just two things, they're actually two ionic compounds. So you have a positive guy and a negative guy, positive guy and negative guy. So whenever you have two ionic compounds, which are obviously made up of a cation and an anion, which is the positive guy, right? The cation, and the anion is the negative guy. And always in a double displacement reaction, what happens is the two positive guys basically switch partners. So in this case, what happens is the A, which has a positive charge, will hook up with the D that has a negative charge. Remember, opposites attract, so two positives like A and C here can't come together. Two negatives like B and D cannot come together. It has to be a positive and a negative coming together. That would mean that our C would then hook up with our negative B, and we make two new ionic compounds here. And remember, as we just talked about, double displacement reactions basically take care of I made a solid or I made water. So what does that mean? It means that when this double displacement occurs, one of these guys, for example, this guy, may make a solid, which is sometimes referred to as a precipitate. Or maybe this guy makes water, which obviously is a pure liquid. And the same thing could be for this guy. If it's not the first guy that makes either the solid or water, maybe the second guy makes a solid or water. So double displacement reactions always follow this pattern. You should always have two ionic guys on the left-hand side of the arrow. The two positive guys will switch partners, and the result of that is either a solid or a precipitate will be made, or water will be made. So let's talk a little bit about aqueous solutions. Remember, as we talked about, I think earlier on in this chapter, aqueous are the guys that get this symbol, and aqueous means a water environment. And pretty much all biological reactions take place in an aqueous environment, and a solution is pretty much what aqueous means. And as I might have mentioned earlier as well, a solution is really a homogeneous mixture. And that means that it is the same throughout. Everything mixes together. And there's really two parts to a mixture. There is the solute, which is the smaller part of the mixture, or the solution. And the larger part is the solvent. So earlier, I think we looked at the idea that water by itself is a pure liquid. And if you take water and you put some solid sodium chloride in there, once again, that salt is going to basically dissolve in the water, and that will give us a sodium chloride solution, which will get the aqueous symbol here, and that is a solution. In this particular case, our solvent would be the water, and our solute would be the sodium chloride. So sometimes people go, how do I know what is the solute in the solution? And there's a very simple way to know what is the solute in the solution. It is actually just the name of the solution. So if you have a sodium chloride solution, sodium chloride would be your solute. If you had a potassium chloride solution, potassium chloride would be your solute. So the name of the solution is pretty much going to be your solute. If it's ionic, for the most part, and I won't say 100% of the time, but pretty close. If it's some type of ionic compound that's soluble, water oftentimes is a very good solvent for it. So water doesn't always have to be a good solvent, but it's a very good solvent for a lot of our ionic compounds, and probably a good chance it is if it's ionic. So let's talk a little bit about electrolytes. And this information, by the way, about electrolytes actually is that little section, if you remember at the beginning of this chapter, in part 1 lecture, there's a couple of sections out of chapter 15 that we're going to kind of address here in this chapter. And this is one of them. So I think off the top of my head, we're looking at like 15.3, talking about electrolytes. And we'll also talk about net ionic equations for 15.6. So we're going to hit a little bit of that 15-ish type material here. So if you want to reference it in your book, there is going to be out of chapter 15. So let's talk a little bit about electrolytes. Electrolytes are substances that when they dissolve in water are able to conduct electricity. And really the reason they're able to conduct electricity is when they dissolve in water, they make ions. So they make either cations, which are positively charged. They make anions, which are negatively charged. And it's those presence of those wonderfully drawn ions here in the solution floating around that helps kind of complete the circuit and help conduct electricity. So if you have something that's an electrolyte, it will produce those ions, and it's really the presence of those ions that help conduct electricity really well. There's also things that are referred to as non-electrolytes, and non-electrolytes will actually still in a lot of cases dissolve, say, in water, but the difference is there's no ions being formed. And because there's no ions being formed, they really don't conduct electricity. Now, there's different types of electrolytes. There are strong electrolytes, which are ionic compounds, for example, soluble ionic compounds, strong acids and strong bases, as we'll talk about, are also strong electrolytes. So what is a characteristic of a strong electrolyte? It will 100% break apart into ions in solution. So it will not stay together. So for example, if you had sodium chloride solution, in actual solution, you would have 100% sodium ions and chloride ions floating around in that solution. You would have 100% of these guys in the solution. None of these guys would still be together, the sodium chloride units. So if you were to really look at that solution, you would have nothing but sodium ions floating around, nothing but chloride ions floating around. You have none of these sodium chloride units still together. So everybody's just going to dump off when they go for a swim, going to produce a lot of ions really quickly. And that's why they're a strong electrolyte, because pretty much it's a ton of ions really, really quickly. And this has effect, for example, on conducting electricity. So when we look at strong electrolytes, like we were just talking about there, and we take something like our sodium chloride, and once again, going to 100% break apart into sodium ions and chloride ions floating around. They're soluble. And as I mentioned before, for example, if this was our sodium chloride solution, if we hooked up some electrodes to a light bulb, you will see it conducts electricity really, really well. The light bulb shines very, very brightly. There's just a ton of ions floating around that solution, and that's going to really conduct that electricity pretty well. There's also weak electrolytes. And weak electrolytes, unlike strong electrolytes, actually will stay together pretty much in solution. So unlike this sodium chloride sort of beaker if we had here, which is pretty much just sodium ions as I drew earlier and some chloride ions basically floating around. When you take something like, let's say, weak electrolyte, say something like hydrofluoric acid. Hydrofluoric acid is actually a weak electrolyte, which means when it does break apart in solution, it will produce some H+ ions and some F- ions. But unlike our strong electrolyte up here, where that's going to be 100% what we have in that beaker, in this beaker, it's actually going to be mainly the HF unit, for example, still together. It will produce a little bit of these guys. So a little of these free ions will be produced. And that means that if we look at sort of our beaker in this case, we mainly have the HF unit, for example, still together here, this hydrofluoric acid. We do have a little bit of H plus and a little bit of F minus kind of floating around, but mainly it's going to stay together. So it will actually still be able to conduct electricity because there's still ions present in that solution. Nowhere near what we have in our strong electrolyte. And I don't really have a picture here, but if we were to have the light bulb here, it would be very dim. So if we had a weak electrolyte, our light bulb would be very dim, and it would still light up, but it would look like almost like it's maybe about to die. It doesn't have a lot of light coming out because it's not going to conduct a lot of electricity, but still able to do so because there's still ions present in that solution. So unlike a strong electrolyte, which is what we see in this actual picture here, where the light bulb is very, very bright, again, if you had a weak electrolyte, it would look very dim and almost like it's dying. Now, another way we could see a little bit of a difference here between our strong electrolyte and our weak electrolyte is actually the arrows that we see in the equation. Now, in a strong electrolyte, it's a one-way arrow. Pretty much 100% everybody is dumping out into the product side. Nobody's going to stay over there on the reactant side. We have actually what is referred to as a reversible arrow in this weak electrolyte. That means this reaction actually has two directions. As it goes from reactants to products in this direction, that is what's sometimes referred to as the forward direction. And what happens is after a while, you will gain enough products that they will decide, let's go back the other way. And the products will actually recombine and head back the other direction and start making some more reactants. And that's what's sometimes referred to as the reverse direction. And perhaps you've heard of chemical equilibrium. If you take Chem 51, you'll hear of nothing but chemical equilibrium. It's pretty much what the class is all about. But chemical equilibrium means that at some point, the rate of the forward direction will equal the rate of the reverse direction. And that is what is referred to as chemical equilibrium. And equilibrium doesn't necessarily mean you have the same amount of reactants and products at that point. It's actually talking about how fast it's going to the product side and just as fast going back to the reactant side. So what happens in that situation is because it's going back and forth at the same rate, everybody pretty much locks themselves into place in terms of where they are in terms of their concentration at that point, because just as quick as you lose some to the product side, it comes right back. So you don't necessarily get the equal amount on both sides of the arrow of everybody, but everybody will maintain where they're at when they reach chemical equilibrium. So that's a big hint as to how you know you have sort of a reversible reaction. And also a weak electrolyte is when you see those arrows heading in both directions. Now you also have non-electrolytes, as we talked about. And those are guys that will dissolve in solution, for example, water, but again, will not produce any ions. So sugar is an example of that there. And sugar will basically dissolve in water. Let's call it aqueous sort of for the time being. And basically there's no ions here. And because there's no ions here, it will not conduct electricity because it basically has no ions present. And that's sort of what we see here. Non-electrolyte, really the light bulb not going on in that particular case. Now we also see pure water over here, our distilled water, and we also see nothing happening here. And that's a really important point. Water by itself, pure water, is actually a bad conductor of electricity. And that is because it's a pure substance. It has no ions floating around in it. Water is covalently bonded together. So when water is in solution, it is all bound together, pretty much no ions. And again, no ions, we're not going to get anything happening here with the light bulb. So you may be wondering, you know, if you shower in the, take a shower and you blow dry your hair, should I get electrocuted? The answer is you probably will get a pretty much shock there, because the water coming out of your faucet there and your shower head, once again, is not pure water. They actually put ions into that water a lot of times to purify it and stuff like that. So it actually has a lot of ions in it, which means it will conduct electricity, which is obviously why we don't use electronic devices there in the shower, so we don't get electrocuted. But technically speaking, if you have pure water, nothing in it, it actually has no ions present and should be a fairly poor conductor of electricity because of that. So strong electrolytes 100% break apart, produce a lot of ions really quickly, good conductors of electricity. Weak electrolytes pretty much stay together, still able to produce a little bit of ions, so still able to conduct electricity, but nowhere near as well as a strong electrolyte. And non-electrolytes, again, pretty much do not produce ions, so they do not conduct electricity. Here's a table from chapter 15, for example, of some strong electrolytes and weak electrolytes. Most soluble salts, and salt is a fancy word for an ionic compound. And again, that's going to be our metal and non-metal together, our positive and negative ion together. A lot of strong acids and strong bases are strong electrolytes, and that's what we see here. We have sulfuric acid, nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid is a strong acid, perchloric acid, and some strong bases, sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. These are some weak electrolytes. So everybody over here is going to kind of 100% pretty much break apart into ions, going to conduct electricity really well. These are our weak electrolytes here, which means they're mainly going to stay together, but will produce a little bit of ions. So all these guys are going to kind of mainly stay together, but will produce, again, a few ions. So this is like acetic acid, carbonic acid, nitrous acid, sulfurous acid, hydrosulfuric acid. That's a little oxalic acid, bromic acid, hypochlorous acid. That's ammonia, which is actually a weak base. And there's our hydrofluoric acid that we talked about last time. So all these guys here will have those kind of two-way arrows, which means, again, going to break apart a little bit in solution, but mainly stay together. So in solution, mainly this guy and a little bit of these guys on that side. And all these guys are pretty much one-way streets. They're all just going to break apart into your ions, your cation and your anion, going to conduct electricity really, really well. So as I mentioned before, water is a effective solvent for a lot of ionic compounds. And the reason for that is when we talk about bonding, for example, one thing that water is what is referred to as being polar. And polar means that when we look at something like water, which is polar, it actually has two sides to it. And what I mean by that is because of the unequal sharing of electrons overall in the water molecule, there is a part of water that's more positive and there's a part of water that's more negative. And actually for oxygen part of water, it's more negative, and the hydrogen part of water is actually more positive. And one of the basic principles of how things interact with each other, how molecules interact with each other, why certain things are soluble in each other and they mix, and why certain things don't mix with each other or kind of play nice with each other, is the basic interaction of almost all things in chemistry is opposites attract. So positive side of one molecule, for example, our compound, is attracted to the negative side of another. And that works really well with the case of water, which is polar. And polar means that it has this unequal sharing of electrons. So it's a polar molecule and overall has some unequal sharing of electrons. And that unequal sharing of electrons creates this sort of positive side to water and negative side to water. And that works really well when something like sodium chloride goes for a swim in water, because when sodium chloride goes for a swim, it produces sodium ions, which are positively charged. Also produces chloride ions, which are negatively charged. So what happens is, and how things dissolve, is the water molecules actually are attracted to these ions. And when water gets near the sodium ion, which is positively charged, it actually aligns itself with its oxygens near it. Because again, oxygen here in water is more negative. So it's got that negative positive attraction that allows it to sort of interact with the water. And water is really good because when the negative ion is present, it actually will align its hydrogen side to it. And that's because its hydrogen side is actually more positive. So the positive side here of water is going to be attracted to the negative side of the chloride. That is why when we dissolve something like sodium chloride in water, we look at it and go, it's gone. It disappeared. And sometimes people think that it actually, some type of chemical change has occurred because we can no longer see the sodium chloride crystals. And that is because all the waters that are present, there is a lot of water in water, as weird as that sounds. There's a lot of water molecules in liquid water. So when you go to dissolve salt in it, what happens is there's just so many water molecules, it's actually able to pluck off these individual ions. When sodium chloride starts out by itself in the solid phase, it is a bunch of these positive and negatively charged ions together in sort of a three-dimensional block. And these water molecules, a bunch of them, are able to come out and grab out these ions. And we help this out, right? When you go to dissolve something like sodium chloride, you give it a little stir, right? And then what's that doing? That's doing a lot of things. It's throwing a bunch of water molecules onto this ionic solid. It's also creating a lot of energy, which is going to help in the dissolving process. So you're basically just littering these ions with waters. And these water molecules, because there's so many of them, are able to keep these ions apart from one another. And to our sort of naked eye, if you will, we no longer could visually see it. Now, when we dissolve something like sodium chloride in water, is it a physical change or a chemical change? And hopefully you know it is a physical change. And it's a physical change because the ions are still there. The sodium chloride are really still there. We just can't see them. There's so many water molecules that get in the way. It also keeps this ion away from this ion. And that's a really important thing because probably one of the most or strongest attractive force that there is that actual attraction between the positive ion and the negative ion. And that's electrostatic attraction. It's one of the strongest sort of forces that there are. But because there's so many waters present, they're able to really keep those ions apart. And that keeps them in the aqueous phase. So this is basically what's referred to as hydration. And this is essentially when we write aqueous next to something like sodium chloride. This is basically what is happening in the beaker. These ions are surrounded by water, it keeps them apart, keeps it dissolved. We can no longer see them. I mentioned earlier that it's a physical change. How do I know it's a physical change? Well, let's say this was a big old beaker. Big beaker there. And let's just say we heated this beaker. That's a wonderful drawing of a Bunsen burner, also again known as a triangle at the end of a line. So use some imagination here. Let me help with the imagination. We'll drop a little red flame on there. Now it's much, much, much better in terms of a Bunsen burner fire. I know I failed art 3 times. It's okay. So when we would start to heat something like this, right, what's going to happen is the first thing that's going to happen is these water molecules are going to start to evaporate, right? So these water molecules are going to evaporate. These water molecules are going to evaporate. And if you continuously heat this, out goes the water molecules in a crazy type of move. And at this point, there would be nothing preventing these two ions from coming back together. And if you did this and you evaporated off all the water, you would see, probably not a red solid, but you would see some, probably if this was sodium chloride, some white crystals or something like that, coming back to sort of life, if you will, and you'll be able to actually see it. So in this case, it's a physical change. When we make a solution, because it's a homogeneous mixture, remember that homogeneous mixtures, just like heterogeneous mixtures, you could always get back the original components by some type of physical means. So in the case here, something like sodium chloride, which is salt water solution, if you were to heat that solution and you wanted to collect the water, you could do something like distillation. But if not, you could just put it in an evaporating dish and let it go off into the air, the water part, and you would see left in your dish the sodium chloride coming back. So not a chemical change here when we make a solution. It's actually, again, a physical change. And when we dissolve something that's soluble in water, they're able to be soluble in water because they have very similar interactions. They're able to interact well with water through that electrostatic attraction, that positive and negative attraction, and that helps it dissolve. So this is really important in terms of electrolytes and some types of reactions we're going to talk about here. As I mentioned before, acid and bases, again, are also electrolytes. So a lot of strong acids, and this is a good list. It was up there a minute ago, but this is a good list of some strong acids. And it's good to know as you go through your chemistry career. Once again, hydrochloric acid. Nitric acid is a strong acid, sulfuric acid, perchloric acid, hydrobromic acid, hydroiodic acid. These are, a good list here of some strong acids. Some strong bases typically have hydroxide in it. And some strong bases can typically be found on the periodic table. If you come down to periodic table group 1 and group 2 on the periodic table, where like sodium and potassium is located, maybe come on over to calcium and kind of come this way, and this way. Any of those guys in group 1 or 2 that has hydroxide in it, again, like sodium hydroxide, potassium hydroxide, calcium hydroxide. These are strong bases, and I remind you that group 1 is the alkali metals. Group 2 is the alkaline earth metals, and the word alkaline means pretty much basic. So anybody there from group 1 and 2, again, starting kind of up that lithium, sodium, potassium, hanging right and up and down for the most part there. In group 2, with hydroxide in the formula, are typically strong bases. So they will completely break apart 100%. So if you had something like sodium hydroxide, which is a strong base, also a strong electrolyte, when it's in solution, it will 100% break apart into sodium ion and hydroxide ion. And that's essentially why it's considered a strong base, because it will 100% break apart in solution. And one of the definitions of what makes something a base is the ability to produce OH minus or hydroxide ions free in solution. So because it's a strong base, strong electrolyte, all it has to do is go for a swim and it will produce a bunch of hydroxide really quickly. And that's why it's considered a strong base. Just like something like hydrochloric acid, when it's in solution, will 100% break apart into H plus and Cl minus. And that means when you have a solution of hydrochloric acid, you have a bunch of H pluses and some Cl minuses. And definition of an acid is something that has the ability to produce free H plus. It's sometimes also referred to as H3O plus. They are the same thing in terms of acid base. For these guys, and producing that free H plus in solution makes something an acid. And something like hydrochloric acid, all it has to do is go for a swim and it will create a lot of free H plus really, really quickly. And that's why it's considered a strong acid. So strong electrolytes are strong bases, they're strong acids, they're also soluble ionic compounds. We're going to talk a little bit about solubility here in just a second. But things that are soluble ionic compounds, which means that they will dissolve in solution or water, are strong electrolytes. Other acids, which are weak acids on weak bases or weak electrolyte, this is acetic acid, also sometimes written as C2H4O2, is acetic acid. Again, we see our arrows heading in both directions, produces acetate and H plus. So in solution, once again, if you had acetic acid, which is the major component of vinegar, you would mainly have this guy all together, but you would produce a little bit of acetate in there. It's an ion, and you produce a little bit of H plus. So because you're able to produce a little bit of H plus, it's still considered an acid. So it meets the basic definition of an acid, which is the ability to produce H plus. But it produces nowhere near the amount of H plus that something like hydrochloric acid would produce, which is a strong acid. But they're both still acids in this case. A weak base, which is probably the most common weak base that you'll come across, is NH3, which is ammonia. Ammonia is a weak base where when it's in water, for example, will produce NH4 plus and OH minus, or sometimes just referred to as ammonium hydroxide. And that means in solution, you mainly have NH3 still together, but still able to produce a little bit of hydroxide in NH4 plus. And once again, it's able to produce a little bit of hydroxide, which makes it a weak base. So NH3 is a weak base. And that also is, again, a weak electrolyte. So the relationship here of electrolytes and what we're going to be talking about here, or have been talking about in terms of double displacement reactions, is if you have something that's considered a strong electrolyte, when it's actually in solution, which is what happens in these double displacement reactions a lot of times, we would expect them to be completely broken apart into ions. None of it's still staying together as whole units. When we have something that's considered a weak electrolyte, like our weak acids, we would expect them to actually stay together and not break apart like our weak acid or our weak base. Why it's important to maybe have a recognition of these strong acids, and one of the questions that maybe somebody might be asking right about now is, how do I know it's a strong acid versus a weak acid? If it is not one of these kind of 6 acids right up here, it's probably a good chance that it's a weak acid. So if you don't see one of those guys, the hydrochloric acid, nitric acid, sulfuric acid, perchloric, hydrobromic, or hydroiodic acid, it's probably a fairly safe bet that it's going to be a weak acid. So again, if we look back at that, where's that table there? I think it's one more back, maybe. There it is. So pretty much, as I mentioned before, if it's not this acid, that acid, that acid, that acid, that one, or that one, these 6 acids, it's a pretty safe bet that it's probably going to be a weak acid. So knowing those 6 is probably easier than trying to remember all the other options for weak acids and stuff like that. So I would say that's a good way to sort of narrow it down for yourself if you ever come across it. All right, that's my list of 6 kind of strong acids. If it's not one of those, it's probably going to be a weak acid. Now for the bases, same idea. If it's not like group 1 or group 2, starting at sodium, potassium, hanging over there to calcium, hydroxide, sodium hydroxide, potassium hydroxide, it doesn't have hydroxide in it, fairly good shot that it's going to be a weak base. So I would say, again, probably the ammonia there, the NH3 is the most common weak base that you might come across. So just kind of knowing that one's a weak base. And if he sees, again, sodium hydroxide, potassium hydroxide, somewhere in that group 1 or 2 with the hydroxide, and probably a good bet that's going to be a strong base, which would make it a strong electrolyte. All right, now we got a little foundation on electrolytes. Let's talk about precipitation reactions. And precipitation reactions are reactions that produce a solid. So these are guys that produce a solid. And what type of reactions are these? These are still double displacement reactions. Which means they will have this same setup as we talked about, an ionic compound plus another ionic compound where we're going to switch partners basically. And we will make 2 new ionic compounds. And in this case, because it's a precipitation, one of these guys are going to make a solid. And that's what's referred to as a precipitate, a PPT, as we talked about, sometimes abbreviated as. But a precipitation reaction obviously accounts for one of the reasons why a reaction takes place, which is a solid is formed. It is a more specific classification of the big umbrella of double displacement. So ultimately, it's still a double displacement reaction. It can be more specifically classified as a precipitation reaction because it makes a precipitate. And that's what we see here in this picture here. A precipitate is an insoluble solid that forms something like this, which is a result of basically 2 solutions being mixed together and some type of solid forms. As I mentioned earlier, doesn't necessarily have to be a rock hard solid. So cloudiness, this yellow solid that really wasn't there before, is an indication of a precipitate or solid. And that is a direct result of those ions switching partners and making new partners on the product side, where again, one of those guys will make a solid. Let's take a look at this one, which is probably what we see here. If we take this reaction here, and first off, this is a double displacement reaction. How do I know this is a double displacement reaction? That's lead to nitrate, which is an ionic compound. So that's a positive and negative guy. That's sodium iodide, which is also a positive negative guy. So right there, that is the only type of reaction that's a double displacement reaction that will have 2 ionic compounds happening. So as soon as you see 2 ionic compounds, you should know it's a double displacement reaction. And you should frankly know that what's going to happen here is these 2 guys are going to get together. And these 2 guys are going to get together on the other side of the arrow. So when we do this, we do form PbI2, which is this yellow solid that we see there in the picture. Now, earlier, if you remember when we were talking about in the first part of this chapter, we're talking about writing equations, and we talked about the idea that it's important to get the correct formula first. So when we look at this molecular equation, which is what we see up here on top, let's just say, for example, we were only given this part of the equation. So let's just say, for example, we were given, hey, we're going to toss together here a little lead to nitrate. And we're going to put it together with a little sodium iodide. What's on the other side? So once again, when we look at this, we should be able to predict that it is a double displacement reaction because that's positive and that's negative. That's positive and negative. So what's important here in terms of writing the equation, balancing the equation? If you remember when we talked about sort of balancing equations, it's important to do what first? It's important to do the equations first. So we want to get the right formulas first. We're not even going to worry about the balancing part. So when we look at these 2 things, we know that they're going to basically switch partners. So what we want to think about here is what are the basic units of each of these ionic compounds. So if we look at the first guy, which is lead to iodide, the basic unit of this guy is a lead with a +2 charge. Now, there are 2 of these nitrates, which is a polyatomic ion, and the basic unit of our lead 2 nitrate is a lead with a +2 charge and a nitrate with a -1 charge. What is the basic unit of sodium iodide? That is a sodium, which is group 1, and that is iodide, which is group 7. So these 4 ions is really what's floating around in that solution. So when you take a beaker and you pour in these 2 solutions, solution 1 are lead 2 iodide, you're dumping in there some lead +2 ions, and you're dumping in there some nitrate ions. When you dump in the other solution, the sodium iodide, you're dumping in some sodium ions, and you're dumping in some iodide ions. These are actually the ions that are in that solution as everybody goes for a swim. So when we want to figure out what's on this side, we want to put these guys together correctly. So what should we do? We know that the positive guy in the first one will hook up with the negative guy in the second one. And I guess yellow is fitting here to highlight with. And if I do that, this is still an ionic compound. So what does that mean? It means, like we talked about in terms of naming, whenever we put something that's an ionic compound together, a positive and negative together, we always want to equal 0 in the charge. That means when this guy that's a +2 comes together with this guy that's a -1, the proper formula should be 1 of the lead and 2 of the iodides. And again, we need 2 of these guys to balance out that +2 charge here. That is the proper formula that we should get. Now, when we look at the other guys that are going to come together, a different highlighting color here. Maybe we'll go with green. We know that the sodium here is going to end up with the nitrate here. I'll do a little green action over here. Maybe I'll do a little green action. And when we put those together, we once again want to think about it equaling 0. In this case, though, that is +1 and that is -1, which means when it comes together, we only need 1 of each of these guys. In this case, this is aqueous. We'll talk about why that is in a second, and that's a solid. That is the proper formula. It is not what a lot of people would write, something like NaNO3 as they try to balance it and also write the proper formulas. So you see here, I didn't worry about the balancing part. All I am concerned with here is getting the proper formulas for our products in this case. Now that I did that, I need to figure out the balancing part and see if it is balanced. And if we look at it, we could see that there's 2 nitrates on the left, 1 on the right. So they're definitely not balanced. And I'm also going to start there as we talked about balancing. So because there's 2 nitrates on the left, I could put a 2 here. And that balances my nitrates, also gives me 2 sodiums, which means I need a 2 there. So what I have just done is the proper way, like we were talking about when we were talking about balancing equations, is if I need to predict what's on the right-hand side of the arrow, what I want to do is make sure I get all the correct formulas down first and then balance it. You do not want to do that together, as I mentioned a number of times in the last video, and I'll mention here again. Otherwise, you will find yourself probably getting the wrong formulas and nothing balancing. All right, so I want to take a moment there just to kind of go through that procedure so that you can see how you should be thinking about completing these formulas. So now that we have this formula, which is really the molecular equation, it represents everybody's formulas written out as their whole units. Now, as I sort of alluded to there in the top right with that picture, what is actually happening when you dump these guys into this solution or this beaker is we got a bunch of ions floating around, basically. So we can actually take this equation and we can actually write another equation which basically describes what is happening in this solution. And as we just said, when we dump these guys into here, so obviously, as we just talked about, we have some lead ions, we have some nitrate ions, we have some sodium ions, and we have some iodide ions floating around in this case. All right, so in this particular case, we could write another equation, which is what is referred to as the total ionic equation, and this describes what's really happening. So in this equation, anything that is a soluble salt, a strong electrolyte, and those are typically guys that have aqueous next to them, will be 100% break apart into ions. Anything that is a solid, anything that's a liquid or a gas will actually stay together. And also anything that's a weak electrolyte will also stay together and not break apart into ions. So if we were to look at this, this is lead 2 nitrate. When this breaks apart, you will get a lead ion that has a +2 charge. You will also get 2 of the nitrate ions. And that 2 that's here actually comes to the front. And that's because this is basically, if we were to break up all the ions that are present, that is basically what we got going on, right? 1 lead and 1 and 2 of the nitrates. This is sodium iodide, which is also a strong electrolyte, and it will give us 2 sodium ions and 2 iodide ions. And that's because this 2 will get distributed to both of the guys behind it. Now, when we get to the other side of the arrow, we have this lead 2 iodide, which is actually a solid. Now, the only way for something to be a solid is it's not really floating around separate from each other. Those ions have basically come together and attached to one another, kind of like what happens with the sodium chloride when we got rid of the water. So in this particular case, what's happening is this lead and this iodide, and really, in reality, there is 1 more iodide floating around as well. That's going to be needed. These guys are going to come together and make this yellow solid. And that's what we see in that other picture, is those guys coming together. And because they make a solid, we actually keep them together. So anything, again, that's a solid, a liquid, a gas, or a weak electrolyte will stay together. So that will stay together. This is a strong electrolyte, which is an ionic compound. And that 2 will get distributed to everybody behind it. And that will make 2 sodium ions and 2 nitrate ions here. So this equation, which is right here, this is what is referred to as the ionic equation, sometimes called the total ionic or complete ionic equation. And it's the equation that basically describes what's happening in the beaker. And anything that's an ion will be floating around freely. And anything that's a solid, liquid, gas, or weak electrolyte will stay together. Now, it is a total ionic equation, which means anything that is ions need to have charges. So that's also something that people mess up on when they do these equations. They do not write the charges. So you do need the charges here because they're ions. Remember that whenever you write a formula for an ion, it should contain the charge. So what happens now that we have this equation? Well, when we look at this equation, especially the ions that are present in the total ionic equation. So here's our molecular equation. That's our total ionic equation. We'll call it TI for its abbreviation there, total ionic equation. When we look at this, we should be able to find ions that are the same on both sides of the arrow. And they should be exactly the same. They should be ions. And in this case, there are 2 sodium ions here and also 2 sodium ions there. There are also 2 nitrate ions here and 2 nitrate ions there. Those are ions that look exactly the same on both sides. They are freely floating around in the solution. Frankly, they are, if we go back to our picture, they're these guys that aren't making the solid. They're the guys freely floating around in the solution, just having a nice time, going for a little float. Nice weather outside, floating around, not really doing much. These guys that we find, which are ions that are found on both sides of the arrow, and by the way, if you do this correctly, they should be there in the exact same amount. So what I mean by that is there's 2 nitrates on the left, there's 2 nitrates on the right. There's 2 sodiums on the left, there's 2 sodiums on the right. When you get to this part, you should always find those spectator ions to be equal on both sides of the arrow. If you find that they are not equal on both sides of the arrow, there's probably a pretty good chance you didn't balance something correctly. And that's really why they are not matching. So that's a good way to check yourself. So they are spectator ions. So what does spectator ions mean? The word spectator means watching. So they're just hanging out. They're really not making any of the important products in this reaction. They're just there to bounce out the charge. They're there to have a nice little float. So what we do with our spectator ions are, when we find them on both sides of the arrow, we basically can cancel them out, because it's like subtracting 2 sodiums from each side, subtracting 2 nitrates from each side. And when we do that, that will leave us really the third type of equation that's important. That will leave us the net ionic equation in this case, and that is what we are left with here. And what is the net ionic equation? The net ionic equation is pretty much exactly what's happening in this reaction to make the product. Remember that one of the reasons why a reaction takes place is a solid being formed. So what is truly happening when you mix this solution with this solution in that beaker, what is essentially happening is the lead ions from the lead 2 nitrate is going to go find the iodide ions, sodium iodide, and they are going to come together to make this yellow solid. I guess that's not so yellow there in my color, but we'll make this yellow solid in this reaction. So you can think of the net ionic reaction as sort of the bare minimum reaction that clearly tells you this is what's happening in this reaction. This is really what is forming. And once again, in this precipitation reaction, which is really a double displacement reaction, it is the formation of this solid, which is the reason why this reaction is taking place. So molecular equation, rewrite everybody's formula complete. No ions, just like normal. Total ionic equation, we break apart those molecular equation into ions. Anything that's a strong electrolyte will 100% break apart into ions. Anything, again, that's a weak electrolyte, a solid, liquid, or gas will stay together and not break apart. And then we find our spectator ions, which should be the ions on both sides of the arrow. And we cancel those guys out, leaving us our net ionic equation, which is ultimately truly what is happening in this reaction. All right, so let's take a look at some of these steps here, which again, is sort of chapter 15-ish, which does tie together with precipitation reactions and double displacement reactions. Once again, the rules for writing our net ionic equations: strong electrolytes break apart into ions. Weak electrolytes, again, would stay together. Solid and gases stay together. And we get rid of our spectator ions, get to our net ionic equation. So you might be wondering, what would happen if you did have, say, a weak electrolyte? So, for example, let's say we had hydrofluoric acid, which, as we know, is a weak electrolyte. And we react with sodium hydroxide, which, as we talked about, is a strong electrolyte. And we will end up with something like NaF and a little H2O. Now you may be wondering, how did I get there? Well, first off, that's a positive negative guy, and that's a positive negative guy, which means we're going to switch partners. So, and so this is basically H plus and F minus. This is basically Na plus and OH minus. So the H plus and OH minus, that's basically two H's and an O. That is water, basically. That is how we get to our water. And obviously our sodium, which is +1, and our fluoride, which is -1. That is how we get to our sodium fluoride here. So what would happen as we would go to our total ionic equation? I'm going to erase a little what I just drew there, so save a little bit on some room here. All right, so now when we go to our total ionic equation, I know that this is a weak acid because I know my 6 strong acids, and that's not one of them. So because it's a weak acid, once again, it's a weak electrolyte, it will actually stay together, and we would not break it apart. Remember, it mostly will stay together in solution. Sodium hydroxide, which is a strong base, is a strong electrolyte, so it will break apart into sodium ion and hydroxide ion. Sodium fluoride, also a soluble salt, will break apart into a sodium ion and a fluoride ion. And our water, which is a liquid, once again, liquid, gas, or solid, will stay together, so we would not break it apart. At this point, what's going to actually happen, that is our molecular equation. That's our total ionic equation. When we get to our net ionic equation, we're going to look for our spectator ions. In this particular case, we got a sodium, and we got a sodium that's exactly the same. And frankly, that's it. Those are the only two that would cancel out. It would leave us HF plus hydroxide gives us F minus and our water. So the difference here is when you do get a, say, weak electrolyte involved in this type of reaction is you probably will only have one spectator ion. You'll keep that weak electrolyte together, which is why you actually only end up with one spectator ion. And then, the rest is kind of very similar. So it'll be slightly different in the outcome. When you do have that weak electrolyte in there, usually you'll be lacking a spectator ion, and you'll still have, obviously, the weak electrolyte still together. But that's sort of how it would work in that situation. So let's talk a little bit about how do we know if we're going to get a solid to form if we come together with certain ionic compounds. And we have to know something about solubility when we do this. And solubility is the idea that if something is soluble, it basically means everything will mix. We're talking about sort of a solid in a liquid, it will dissolve. We're talking about two liquids, they'll mix together. If something's insoluble, they won't mix. You typically will get a solid that forms. Now, usually when we talk about solubility, it's broken up into sort of 3 categories. It's broken up into soluble, which means you would not expect a solid to form. And those are guys, when we look at equations, have the aqueous symbol next to them. So things that are soluble typically will have that aqueous symbol. If things are insoluble, they typically will get the solid symbol next to them. Now, there is also another category which is slightly soluble. And in most cases, slightly soluble is usually considered to be more like being insoluble. So you see something that's slightly soluble, it really is what the name sounds like. A little bit of it will dissolve, but most of it will not dissolve. So most people will consider slightly soluble to be leaning more towards being insoluble. So there's actually solubility rules that help us make these sort of decisions. So what we're looking at here are things that are typically soluble. Anybody in group 1 is going to be soluble. So if you have a formula where there's somebody from group 1 in it, it's going to be soluble. You're just going to lay pretty much the aqueous symbol next to it. Anything that has ammonium in it, NH4 plus, it's going to be soluble. There's no exceptions. Things that contain nitrate, chlorate, or perchlorate will also be soluble. So as soon as you see those in the formula, you know it should get the aqueous symbol. Things that contain chloride, bromides, and iodides are soluble, but there are some exceptions. So if you have something that has chloride, bromide, or iodide, they will get the aqueous symbol. But if one of those three guys are hooked up with silver, that's mercury 1 or that's lead 2, it will then become insoluble. And those guys would actually get the solid symbol. So sort of the opposite. Most sulfates are soluble except for calcium and silver, which are slightly soluble. Barium and mercury 2 and lead are insoluble in this case. So most of these guys will get aqueous unless it's one of these three. They'll get a solid symbol next to it being insoluble. Now there's certain things that are insoluble. So these are guys that typically will get the solid symbol next to it. Hydroxides, except for group 1, barium, calcium hydroxides are slightly soluble. Carbonates, phosphates, and sulfides are typically insoluble, except for group 1 and ammonium. So that group 1 and ammonium is pretty much the other rule that are soluble in everything. Here's another solubility table, just kind of set up a little bit different, but kind of the same idea. So anybody that is on this side should get the aqueous symbol and would be soluble. Now, unless it's somebody on this side, they would then be solids. So anybody on this side should be solid, but if it's somebody on this side with somebody on the left there, they will be aqueous. So how does this work? So for example, if we looked at, say, some sodium chloride plus some silver nitrate. Now, first off, I'm going to get the right formulas here. So I know that this is a positive guy, negative guy, positive guy, negative guy. So right there tells me it's a double displacement reaction. So I know it is. So our guys are going to switch partners. So we're going to switch this way and we're going to switch this way. So sodium here is +1. It's going to hook up with nitrate, which is -1. So when I put those together, a little NaNO3, one of each of them. My silver is +1. My chloride is group 7, which is -1. So when these guys come together, I will get silver chloride. We want to now make sure it's balanced. There's one silver on each side, one nitrate on each side, one sodium on each side, and one chloride on each side. So it is balanced. And again, get rid of some of the scribble here. So now that we have the equation, now that it's balanced, we could actually figure out the solubility by using the solubility rules here. So here we go. We're going to first look at sodium chloride. Sodium is a group 1, which means there are no exceptions and it should always be soluble. So as soon as I see sodium in that formula, I really don't have to look any further. I know it's going to be soluble and this guy should get the aqueous symbol. Now I look at silver here and maybe I don't see it on the left, but I do see nitrate on the left and nitrate's right here. Nitrate is soluble and there's no exceptions, which means as soon as I see nitrate in the actual formula, I know it's soluble and it should get the aqueous symbol. Now coming to the right-hand side, sodium, it's really as far as that has to look. That is group 1, no exceptions. That means it should be soluble. I could also look at nitrate in this case, which is also soluble in everything. Now over here, I may not see silver, but I do see chloride. Chloride's here, and that is soluble in everything, but there are some exceptions. And this happens to be one of the exceptions. It's actually chloride with silver, which means instead of it being soluble, because it's one of the exceptions, it's actually going to be insoluble. And that is going to be my solid that is formed in this case. This would be considered a double displacement reaction. This would also be considered a precipitation reaction. And once again, one of the reasons why this reaction is taking place is that solid being formed. If we were to take this all the way through to our total ionic equation, that would be a sodium ion plus a chloride ion, as that would break apart completely. Our silver nitrate would also break apart completely. Our sodium nitrate on the other side would break apart completely. And our silver chloride is going to go underneath, will stay together as it's a solid. That would be our total ionic equation. So this would be our molecular equation. This would be our total ionic equation. Looking for spectator ions, we have a sodium on the left to match a sodium on the right. We also have a nitrate on the left to match the nitrate on the right. Those are our spectator ions, which we could cancel out. And that would leave us the net ionic equation, which is really what is happening in this reaction. When you dump that silver nitrate, it's the silver ion going and finding the chloride ion from the sodium chloride. And those guys are going to come together to make silver chloride, which is a solid. And one of the reasons why a reaction takes place, this kind of white solid that occurs, and that would be our total ionic equation. So this is how you can use solubility rules to predict what's going to be a solid and what's not going to be a solid. Since I did one, why don't you try one here? Let me just get rid of everything on here. Perfect. And let's say, why don't you write the molecular equation, the total ionic equation, and the net ionic equation for what happens when we put together. Very good question here. Let's see, when we put together, what do we want to go with here? Let's do iron 3 chloride and sodium sulfide. All right, so why don't you take a few minutes, use these solubility rules or the ones on the previous page, which is kind of the same. Write the completely balanced molecular equation, the balanced total ionic equation, and the net ionic equation, and figure out the spectator ion. So take a few moments there and see what you come up with here. Okay, so let's take a look. Once again, you should recognize this as a positive negative guy, positive negative. So that's a double displacement reaction if we've ever seen it. So again, we just want to take the basic units of each of these guys. So this guy really is an iron with a +3 charge, and this is a chloride. Basic unit of this guy is a sodium ion and a sulfide ion. So remember, in this type of reaction, our positive guys are going to switch partners. So these guys are going to come together, and these guys are going to come together. So that's what we want on the other side here. So when I take the iron, which is +3, and put it together with sulfide, which is -2. Common number there is 6. So I will need 2 of the irons and 3 of the sulfides. And when sodium comes together, that's +1 and -1, which means I just need 1 of each of these. So again, this is the proper formula here. I am not worried about the balancing aspect of it at this point. I am, again, just getting the proper formulas down. Now that I do have the proper formulas down, we are ready to do the balancing part because it's not balanced. And hopefully we don't erase the sodium there. We'll bring my N back. Okay, so now we need to balance it. So here, maybe we want to do a 2 there. That gives us 6 chlorides, maybe a 6 there, maybe a 3 there. Bad, I think. Going kind of quick, but I think I got it there. So 2 irons on both sides, 6 chlorides on both sides, 6 sodiums, and 3 sulfides. So this is my balanced molecular equation. I can now use my solubility rules here to figure out what's going to be soluble, what's going to be insoluble, if there is one. So iron 3 chloride, that would be chloride. They are soluble in everything, which means it should be aqueous, unless it's one of these 3 things. In this case, it is not. So that should be aqueous. That's sodium, so that's pretty much as far as I need to look. That should be aqueous. Now going on the other side there. We have iron 2 sulfide. So remember, sulfide is insoluble, which means it should be a solid, unless it's group 1, which iron is not, or ammonium, which it is not. So that means we should get a solid here. And lastly, sodium really is as far as we need to look. That's soluble in everything. So that should be soluble. So again, this is how we can use our solubility rules to figure out what's going to be soluble and what's going to be insoluble. Now we could write our total ionic equation. So this is a strong electrolyte, so it's going to break apart. We do need to distribute that 2 in front. So that's going to give me 2 of the iron 3s. That's going to give me actually 6 of the chlorides. And that is basically the 2 in front times the 3 in the back there. Our sodium sulfide will break apart, so that's going to give us 6 of the sodium ions, also distributing the 3. That will give us 3 of the sulfide ions. These are ions, so again, everybody has charges. Going to the other side, remember our solid will stay together. Our sodium chloride will break apart, so again, that 6 gets distributed. 6 sodiums and 6 chlorides in this case. That is our total ionic equation. Looking at it, we can now find our spectator ions. Looks like 6 chlorides on both sides and 6 sodiums on both sides. Those are our spectator ions. Again, we're going to get rid of those, and that's going to leave us our net ionic equation. We get rid of those. And that's going to leave us here our net ionic equation of a couple of iron ions going to come together with a few of our sulfide ions. And that is going to make our iron 3 sulfide here in this case. Once again, solid being formed, precipitation reaction, one of the reasons why a reaction takes place. So hopefully you're getting the hang of this, how the solubility tables fit into our molecular equation, total ionic equation, net ionic equation, and obviously how electrolytes fit in there. So again, strong electrolytes going to break apart in these equations. Weak electrolytes going to stay together. Also, total ionic equation, net ionic equation, once again, need to have the charges on the ions. All right. So let us try one here. Why don't you do this? Let's write the net ionic equation for this reaction. So actually, once you start with finishing the equation, balancing it, total ionic and net ionic. So why don't you give it a go and see what you come up with.
Hello there. I told you I'd pop back in again. I wasn't kidding, a little on the long side this chapter. So let's do a little stretching here. Probably good time. Stretch there, stretch there, stretch there, stretch there, stretch there, stretch there. Always good to stay loose as you're doing chemistry. All right, back to the lecture.
Okay, let's take a look. Once again, we should recognize positive, negative, so double displacement reaction. Again, going to switch partners. So once again, we want to think about the basic units here. So barium chloride is a barium with a +2 charge and a chloride with a -1. Sodium sulfate is a sodium ion and a sulfate ion. So once again, we want to put these guys together correctly. So when those two come together, that's a +2 and -2, which is going to give us BaSO4. And this is a +1 and -1, which means, again, NaCl. So once again, we're not worried about balancing it. We want to get the right formulas down. Now we definitely should be worried about the balancing. So we do need to do a little balancing. And I believe in this case, just a 2 right about there should do the trick. And that should give us 2 sodiums and 2 chlorides, 1 sulfate, 1 barium. At this point, we can use our solubility rules. And if we looked at our solubility rules, we should have an aqueous there because that is sodium. And that's one of the exceptions there. And that's going to give us a solid for our barium sulfate. So this is our molecular equation here. Once again, we're going to break this apart properly for our total ionic equation. So that barium chloride will break apart into a barium ion. And again, that 2 will come to the front, and that will give us 2 chlorides. The sodium sulfate will break apart. The 2 will come to the front, giving us 2 sodium ions and a sulfate ion. And our barium sulfate will stay together as that is a solid. And our sodium chloride will break apart, so that 2 does get distributed to each of the guys there. And this is our total ionic equation here. So hopefully we could see it, and we did see it, that our chloride in this case on both sides and our sodium here on both sides are our spectator ions, right? So these are our spectator ions. We again cancel those guys out, and what we are left with is our net ionic equation. And that means in this reaction, it is the barium ions floating around in that beaker, going to go find themselves some sulfate ions, and they are going to come together to make this white solid here of barium sulfate. And again, that is ultimately what is happening in this equation, or this reaction. All right, let's take a look at another one here. Write the whole deal. That's a little sodium carbonate and hydrochloric acid. Get the net ionic equation of what's happening here. So I want you to do all 3 equations as well. So take a moment and see what you come up with. Okay, so let's take a look. Once again, positive, negative, positive, negative. So double displacement reaction. So once again, we're going to think about the basic units of these things. So that sodium carbonate is a sodium ion and a carbonate ion, which has a -2 charge. That's hydrochloric acid, which means it's H plus and Cl minus. Once again, we're going to switch partners. So those guys are going to come together, and these guys are going to come together. We want to put them together in a proper way. So sodium is +1 and chloride is -1. So we just need 1 of each of those guys. And our H is +1 and -2, which means we actually need 2 of those guys. There, the H's, to balance it out. Now, this is going to be aqueous. This is also going to be aqueous. And we do need perhaps a balancing here of 2 and a 2. And I think that should be good. Now, this is one of the things that can happen in a double displacement reaction. You're like, there's no solid or liquid that was formed here, right? And that is because this is actually a double displacement reaction where we will produce a gas indirectly. What will actually happen in this case is this carbonic acid will not stay around long at all. And it will go through what is referred to as a decomposition reaction. And it will actually form CO2, which is a gas, and water. So this guy will actually break apart into CO2 and water, which means we could write this reaction as Na2CO3 plus 2HCl goes to 2 of the NaCl and CO2 and water here. Plop, plop, fizz, fizz. So we should still be balanced. We got 2 hydrogens. We got there 3 oxygens, a carbon, and a couple of sodiums there. And this would be actually our molecular equation. Now, when we go to our total ionic equation, we will get 2 sodium ions. We'll have a carbonate. Chloric acid will break apart into H plus and 2 Cl minuses, once again distributing that. This will give us 2 sodium ions on the other side and 2 chloride ions as well. Now our CO2 will stay together as it's gas. Get my eraser. And also my water will stay together here as well. All right, so spectator ion wise here, sodium and chloride, which I forgot to put the 2 there. There, we got it. There we go. 2 there and 2 there. We'll cancel. That's going to leave us our net ionic equation, which is basically this H plus and some carbonate. We'll make a little CO2 and some water. So a little different than some of the other ones, but this is what we would end up with here. And we'll make a little CO2 and water. So a result of some double displacement reactions actually is you can make a gas. You can actually make a gas directly sometimes. And a lot of times, sometimes a gas can be generated through a secondary reaction, which is one of the products we'll go through a decomposition reaction. All right, so let's take a look at another one here, I think. So once you give this one a go, we'll write the whole reaction there of hydrobromic acid with potassium hydroxide and molecular equation, total ionic equation, and net ionic equation and see what you come up with here. Okay, let's take a look here. So we've got everything in words, so we want to start with the right formulas here would be good. Hydrobromic acid is HBr. Remember, hydro and in terms of acids means no oxygen, so that's how we know it's HBr. Potassium hydroxide, that's K with a +1 and OH minus with a -1. Going to give us a little potassium hydroxide. Once again, this is a positive and positive negative. There you go, positive negative. So H and OH will come together to make water. And K plus and Br will come together to make KBr in this case. And again, water is a pure liquid. And potassium is group 1, which means it's soluble in everything. So that is why it gets the aqueous symbol. Same thing down here. Potassium hydroxide is soluble, and that's soluble as well, as they're both strong electrolytes. That means we want to balance the equation. And in this case, I think we are balanced. So we're good to go. Now we want to break it apart. So since that's one of our 6 strong acids, we know that this will break apart into H plus and Br minus. We also know that KOH is a strong base, which is a strong electrolyte. We'll break apart into K plus and OH minus. Once again, here our water is going to stay together, and that will give us H2O. And our potassium bromide is a soluble salt, which is an ionic compound. We'll break apart into these 2 guys here. Looking for spectator ions here, Br minus, K plus, exact same on both sides, cancel out, leaving us ultimately what is happening in this reaction is the H plus from the acid, which is this guy. And this guy is our base. The OH minus from our base are going to come together to make our friend water. And if you remember, that is another reason, one of the 3 main reasons why a reaction takes place, formation of water, which we just did here. So unlike the other one, which was formation of solid, here is actually formation of water, which is one of the reasons why it takes place. All right, so hopefully we get an idea how to write molecular equations, total ionic equations, net ionic equations. You obviously need to be able to do all 3 of those things and figure out the spectator ions. Either if the formula is given to you, the equation, or you might have to even figure out the back end of the equation like we've been talking about. Let's talk a little about acids and bases, which is kind of what we were just looking at in that last example. Acids have sour taste. They cause litmus paper to change color. So typically if you're using litmus paper, a lot of times we use it to figure out is a solution acidic, basic, or neutral. And if the litmus paper turns red or stays red, is typically acidic. Could also react with metals to produce hydrogen gas, which we'll talk about a little bit later on here in this chapter. And strong acids can conduct electricity because they're strong electrolytes. Bases have a bitter taste. They feel slippery. A lot of soaps, drain cleaners or bases, they actually change litmus paper to blue. So if you're using litmus paper and it turns blue when you put a solution on it, you know it's basic. And they also conduct electricity as they are strong electrolytes as well. So an acid is a substance that has the ability to produce free H plus ions, which are sometimes referred to as protons. And that is because hydrogen, if we remember, has one proton. It has one electron. And it has no neutrons. One of the only elements that does not have neutrons. So in order for something to become positively charged, it has to lose an electron, and it doesn't have a neutron, which means it has a proton. So in acid-base chemistry, H plus is sometimes referred to as a proton. Also, as I mentioned before, in acid-base chemistry, H3O plus, which is known as the hydronium ion, and H plus are essentially the same thing, and they're used interchangeable. They represent really the acidic part of the solution. I personally use H plus most of the time, but anywhere I kind of use H plus, you can put H3O plus in terms of acid-base chemistry, and it basically means the same. As we talked about before, our strong acids are hydrochloric acid, nitric, sulfuric, hydrobromic, perchloric acid are going to be strong electrolytes, again, 100% brick parts. So if we had nitric acid in solution, pretty much 100% of what you have in that solution is a bunch of H plus and nitrate ions floating around. You have none of the HNO3 units still together. That's why, again, it's considered a strong acid, able to produce a lot of H plus really quickly. Bases, on the other hand, are things that have the ability to produce hydroxide ions in solution. And we're talking about really free hydroxide ions here. So again, sodium, potassium hang over there to calcium, come down on the periodic table in group 1 and 2. Any of these guys with hydroxide in them are typically strong bases. And much like I talked about before, sodium hydroxide in solution will 100% break apart into sodium ions and hydroxide ions. So once again, if you drop that into solution, a lot of sodium ions being made, but more importantly, a bunch of free hydroxide ions being made. And that's what's going to make it a basic solution and also a strong base. So when we take a reaction of a strong acid and base, and these are sometimes referred to as acid-base neutralization reactions, no matter what strong acid or strong base that you put together, the ultimate reaction that is taking place is really the formation of water. So for example, if we did take hydrochloric acid and sodium hydroxide, this is an acid-base neutralization reaction. This is also a double displacement reaction. So once again, we're going to go this way and we're going to switch partners. That is going to give us our water and some sodium chloride. And whenever you take a strong acid and strong base together, you always pretty much make two things. You make what is referred to as water and what is referred to as a salt. And a salt is just an ionic compound, basically a metal and a non-metal together, positive, negative guy that's happening here. Where's the water come from? Frankly, the water in a strong acid, strong base situation, H always from the acid, OH from the base is basically where our water comes from. So that is pretty much always where the water will basically end up from. The salt is really the other two guys that are there. So if we were going to our total ionic equation, we would have our H plus, our Cl minus, our sodium with a +1, our hydroxide, -1, water will stay together, and our sodium chloride will break apart into Na plus and Cl minus. Spectator ion here, chloride on both sides, sodium on both sides, going to cancel out, leaving us our net ionic equation of, surprise, surprise, a little H plus from the acid, getting together with the OH minus from the base. They have a very high affinity for each other to make water. Once again, one of the reasons why a reaction takes place is the formation of water. So acid-base reactions or acid-base neutralization reactions, along with precipitation reactions, fall under the category of double displacement reactions, and they take care of, as we can see in these examples, 2 of the 3 reasons why a reaction takes place: formation of a solid and formation of water in this case. You can put together any strong acid and strong base together. You could go through all the total ionic equation and get to the net ionic equation, and you will always hit this guy right there, like we did here on the bottom. You always hit basically water being formed. So unlike maybe a precipitation reaction where you could actually see the solid being formed, sometimes you can't really see the water being formed, but it is being formed, and that's really the reason for it. So here's basically what we just went over there, and our water being formed. Here's a couple other examples. Once again, we do always make a salt and water in these reactions, and in this case, this is obviously our waters in this category, and these are both our salts in each of these examples. And if you went through the total ionic, non-ionic for this equation and this equation, you would pretty much both hit H plus plus OH minus makes water. I would say most of the time the salt is your spectator ions, and usually they're going to be soluble and aqueous. It is possible that the salt may be insoluble, but most of the time it probably is going to be a soluble salt. So to summarize, here are double displacement reactions, cover more specifically precipitation reactions, which is a more specific classification of that, which accounts obviously for solids being formed, and also acid-base reactions or acid-base neutralization reactions, which covers basically water being formed. So double displacement, once again, sort of the big umbrella of classifications, more specific classifications of double displacement reactions being a precipitation reaction and also an acid-base reaction. And they cover, again, 2 of the 3 reasons why a reaction takes place. All right. The next type of classification of reactions that we're going to talk about are redox reactions, which are sometimes referred to as oxidation reduction reactions. These are what are referred to as redox reactions. They always occur together. So oxidation means that somebody has lost electrons or will lose electrons. And reduction means that somebody will gain electrons. So sometimes people remember this like Leo the lion goes grr. So loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You can put Leo the lion on the oil rig and he goes grr. You don't have to choose. You can use them both. So what does this mean? It always happens together. So if there is something that gets oxidized that loses electrons, there will always be something that gains the electrons. So this type of reactions account for the third thing that occurs when a reaction takes place, which is transfer of electrons. And it may not be obvious to you sometimes that it is happening, but it is ultimately what's happening is a transfer of electrons, which is a redox. So how do we know if something is sort of losing electrons, gaining electrons, being reduced or oxidized? There's actually a really simple way to do it. You could use a basic number line. And when we look at it's really known as oxidation states are numbers, but you could think of it as charges. So when we look at the arrow of something that started on the reactant side to what it ended up on the product side, we look at really its oxidation number, but we'll call it charge here. And if it loses electrons, that means it has to actually become more positive. And that's because it has more protons than electrons, right? So if you find yourself on this number line, when you look at the charge of something on the left-hand side of the arrow to the right-hand side of the arrow, and it's moving in this direction, the more positive direction, that thing is going through oxidation. It is losing electrons. Now, when somebody gains electrons, which happens with reduction, is they're gaining more electrons, which means they're actually going to become more negative because they have more electrons than protons. And that means that they would actually be moving on the number line in the negative direction. And that would be something that is going through reduction. So if you could kind of figure out, again, really what is the oxidation numbers or states or charges of everybody on each side of the arrow, you could actually figure out what's being oxidized and what's being reduced. So let's take a look at some of this here. For example, here, if we look at sodium metal and some chlorine gas coming together to form sodium chloride, we could figure out what is happening here. So the first thing is, when something is by itself, when an element is by itself uncombined, it really has no charge and no oxidation state, which means sodium metal by itself has no charge. Chlorine gas, that's naturally how it comes. It really has no charge. Remember, things really only get charges when like metals and nonmetals come together to make ionic compounds. That means on the right-hand side here, these guys actually do have charges. That's a +1, and this guy's a -1. So if we can figure this out, we can actually figure out what is happening here by, again, using our little number line. So if we were to look at the sodium first, the sodium is starting right here at 0. And on the right-hand side, it's actually ending at +1, which means it is moving in that direction. It is becoming more positive, which means it is going through oxidation. So we know that this guy is actually going through oxidation. You want to know the good thing about oxidation reduction is if you could figure out what is going through oxidation, by default, the other guy has to be going through reduction, and vice versa. You can figure out what's going through reduction. By default, the other thing has to be going through oxidation. Now, we can also figure it out for the chlorine. The chlorine is starting at 0, which is here. And it is ending at -1. So it's actually moving in this direction, becoming more negative, and that agrees with what we just said. It is going through reduction. So what is essentially happening here is the sodium is dumping off its electrons to the chlorine. And at that point, they both gain a charge, and they're going to make that sodium chloride. So this is a redox reaction. It's an oxidation reduction reaction. It's also the formation of sodium chloride. But what is ultimately happening here is our transfer of our electron, the third reason why a reaction takes place. So if we look at this here, again, this is an oxidation reduction reaction. And again, always between a metal and a non-metal, pretty much the metal is always going to be the one who's going to lose electrons because they typically become positively charged. And our non-metals are going to be the ones that gain electrons and become negatively charged. We look at another reaction here. Here is magnesium going to magnesium oxide. This is magnesium by itself, uncombined, actually has a 0 charge or oxidation number. That is naturally how oxygen comes by itself. Also has a 0. But when this metal and non-metal come together, that's an ionic compound, and they will have charges. The magnesium is +2, the oxygen is -2. So if we think about our number line and what's happening here, magnesium is starting at 0, which is here, and it's ending at +2, which means, again, it's moving in a positive direction and it's going through oxidation. The oxygen is starting at 0, and it is going to -2, which is heading in this direction, which means it's going through reduction. And again, this is a transfer of electrons heading in this direction. And electrons are being transferred. We can actually represent this by 2 types of reactions or equations to represent what is happening here. So we have our transfer of electrons, and I'm just going to look at this slide here, which I think has the same thing. We can actually write 2 reactions, which are sometimes referred to as half reactions. And in a half reaction, it shows sort of what is going on. And what's happening here is this magnesium is going to give away some electrons. And this is what is referred to as the oxidation half reaction. And in an oxidation half reaction, we find electrons on the product side like they are being given off. And this is oxygen gaining those 2 electrons. And this is the reduction half reaction. And it's gaining those electrons. So in a reduction half reaction, we typically see electrons as a reactant. Why are they called half reactions? Because frankly, if you add those reactions back together, the electrons should always cancel because they're being transferred from one to the next. Everybody on the left-hand side stays on the left-hand side. Everybody on the right-hand side here stays on the right-hand side. And that gives us our overall reaction. So half reactions are sometimes written for these things. You may also be wondering, why is it on this guy? 4 electrons. Is a magnesium a +2 charge? And you are right, it is a +2 charge, but there's 2 of them, which means each of these magnesiums here are going to give up 2 electrons, right? And that is how they become magnesium with a +2 and magnesium with a +2. 2 electrons, 2 from each, gives us a grand total of 4 electrons in this case. Same thing with the oxygen. Oxygen makes a -2 charge, and O2 means there's really 2 oxygens, right? And each can achieve and accept those 2 electrons and become a -2 charge each. Now, we're not going to get too much into this, but as you continue on with chemistry, there's a few different definitions of oxidation and reduction. And a lot of times we may use oxygen or hydrogen to help us understand what is going on in terms of oxidation and reduction. Most of the time in general chemistry, like this class or the next couple of classes that you take, you really look more at electrons. But a couple other definitions of oxidation and reduction. Oxidation, as we just talked about, is when you lose electrons. It also can mean that you gain oxygen from reactants to products or lose hydrogen from reactants to products. Those are 3 definitions of oxidation. Reduction has similar definitions. It is the gaining of electrons, as we talked about. It is the loss of oxygen as you go from reactants to products. It's also the gaining of hydrogen as you go from reactants to products. So sometimes in things like organic chemistry, for example, it's much easier to follow hydrogen and oxygen than it is in, say, general chemistry or inorganic chemistry. So that's where these definitions sort of come into play. But for us, pretty much it's going to be the electron definition. And probably when you go to the next class, it'll also be electron definition. But we can look at the oxygen definition here. For example, we have sulfur has 2 oxygens here, and over here gains some oxygen. So the sulfur, as it goes from here to here, has gained oxygen, and that means that it's going through oxidation. And by default, this would be reduction in this case, going from basically oxygen to no oxygen on the other side. So those are a couple other definitions. Probably don't have to worry too much about it for our class. But again, the electron definition, losing electrons or gaining electrons, are really the ones you should probably focus on. So now that we talked about redox reactions and we talked about sort of double displacement reactions, there is, again, a more specific way that we could classify all these reactions. And again, it's based on these 3 things happening: solid being formed, water being formed, or electrons being transferred. So earlier on, we saw under our big umbrella of double displacement reactions, we can more specifically classify a reaction as a precipitation reaction. And again, we recognize this as 2 ionic compounds. And again, it is a solid that's being formed, which makes it a precipitation reaction. And our potassium and nitrate come together, which is what we see here. and our barium and our chromate come together, which is what we see here, right? Our sort of double exchange. And again, this is under the big umbrella of double displacement, more specifically our precipitation reaction where we are switching partners. And again, I think we just talked about it there. We got our potassium going to hook up with our negative nitrate, which makes our potassium nitrate. And again, here, our barium, which is positive, will hook up with our chromate, which is negative, make our barium chromate. Again, that formation of the solid is what's considered a precipitation reaction, which again is a more specific classification of a double displacement reaction. Formation of a solid, again, being one of the reasons why a reaction takes place. Here's our acid and base reaction, which is again sometimes referred to as acid-base neutralization reactions. Acid-base neutralization reactions, again, because water is essentially formed, still under the double displacement category, as we talked about. More specific classification, acid-base reaction, positive, negative, positive, negative. Once again, switching partners. And our H and OH coming together to make water. Once again, the H plus from the acid coming together with the OH minus from the base to make the water. And our salt, right? The other two guys coming together. So that is our salt right there. And that makes our water and salt that is formed. Once again, the salt being just an ionic compound. Now, those two were double displacement reactions. We're now going to look at basically redox reactions here. So these fall under the big umbrella of redox. So that is what we see here. This is a redox reaction. Once again, if we look at it, that is 0 and 0. Those are two elements in their natural state. When they come together here to make this ionic compound, that's a +1 and a -1. So once again, if we follow our little number line, our lithium is starting at 0 and ending at +1, which is heading in this direction, becoming more positive. So it's going through oxidation. Once again, metals should always be the one going through oxidation when they're involved with a non-metal. And our fluorine, which is -0 or 0, -0 and going to -1, that sounds better, is a reduction reaction occurring here. And again, our non-metal should always be the one being reduced. So this is definitely a redox reaction is taking place. In this equation, this is also a redox reaction taking place. This is 0. That is +1 and -1. That is 0. That is +2 and -1. So if we look at this on our number line, we could see it actually is a redox reaction happening. The zinc is starting at 0 and ending at +2. The zinc becoming more positive, so it's going through oxidation. The hydrogen here is actually starting at +1 and ending at 0, the H plus. And it's actually becoming more negative. It's going through reduction. What is happening with the chloride? Chloride is starting at -1 and ending at -1, which means nothing's happening to chloride. It's actually just the hydrogen and the zinc here that are exchanging electrons. So it's really the zinc sending electrons to the hydrogen in this case is really what's happening here. So this reaction that we're looking at is also classified as a redox reaction, but it is also more specifically classified as a single replacement reaction. This is a single replacement reaction. And in a single replacement reaction, it is different than a double displacement reaction for a couple of reasons. We typically have a metal. So if this is a metal and an ionic compound, and the metals by itself, it doesn't have a charge, but when metals do gain charges, they become positively charged. And when they would come in, they will actually kick out the positive guy. So metals will typically become positively charged, come in and kick out the positive guy. The result of that is it will make a new ionic compound where it will now gain a charge. and it will hook up with the negative guy. And our guy that originally was there will come out and actually have no charge. You could also do this with a non-metal. And if this has no charge, if you have a non-metal by itself, this is an ionic compound. The non-metal will actually kick out the negative charge, because that's typically what non-metals make when they make charges, is negatively charged. And it will make a new ionic compound, where this guy will then get a charge, and it will take this guy out with no charge. So this is different than a double displacement reaction in a couple ways. First off, double displacement has 2 ionic compounds. This has only 1. And so that's the main difference. By the way, just while we're talking about redox and we were just looking at these double displacement reactions are not redox reactions. So there's no electrons being transferred. Everybody has the same charge on both sides of the arrow. So for example, if we look at this reaction here, really that's +1, -1, +1. OH is -1. This is minus, this is +1. This is -2. This is +1. This is -1. Really, this is -2 and +1 here as well. So everybody has the exact same charge on each side. Nothing's changing. There's no electrons being transferred. So also very keynote to point out, double displacement reactions, which fall under the big umbrella, also are precipitation reactions and acid and base reactions. Those are not redox reactions. There's no electrons being transferred. So they are only resulting in solids and water being formed, but definitely not a redox classification. Just like redox reactions are not classified as double displacement reactions, they involve electrons being transferred. So that's a really important distinction between those two as we look at here. So how do we know if this reaction will take place? Well, this is what's referred to as an activity series. And this is a general activity series for metals. And typically you find hydrogen somewhere around here. And how this table sort of works in a sense is anything higher on the list is more reactive than anything lower on the list. So when we look at these single replacement reactions, in order for this metal, for example, to come in, for this reaction to take place, or even for this non-metal to come in, it needs to be more reactive than what it's replacing. So if it is more reactive than what it's replacing, that reaction will actually take place. If it happens to be less reactive than what it's replacing, then it will not take place. So that's where this activity series comes into play. Anything higher on the list will replace anything lower on the list, and anything lower on the list will not replace anybody higher on the list. Now for non-metals, a lot of times it's the halogens, which is group 7 on the periodic table. And that's pretty much what group 7 looks like. And reactivity increases as you go up. So fluorine is more reactive than chlorine and bromine. So for example, if we had zinc and we try to replace it with hydrochloric acid or hydrochloric acid, this is a ionic guy and this is a guy with no charge. So I know it's going to be a single replacement. The zinc will come in and kick out the hydrogen. I find zinc, which is higher on the list than hydrogen, which means this reaction will take place. The zinc will then gain a +2 charge, which means I will actually end up with zinc chloride. And that's why I need 2 of the chlorides, because zinc has a +2 charge. The hydrogen will come out as its normal element, and that is again hydrogen gas. And that is going to be the bubbles that you would see when you do this reaction as that formation of the gas happens. So this is a single replacement reaction. We want to do some balancing, so we'll put a 2 there. And I think that's all we need. So this is a single replacement reaction, which falls under the category of redox reactions, the big umbrella. And it's still a redox reaction. The zinc here is 0 to +2, and the hydrogen is +1 to 0. So once again, if we were to look at our little number line, plus and minus, Zinc going from 0 to +2, becoming more positive, so it's going through oxidation. The hydrogen here, once again, +1 to 0, becoming more negative and becoming through reduction. The chloride here is actually just a spectator ion. And you could actually write a total ionic equation like we did for our double displacement reactions. And if we do that, we will end up with something like this. We'll jump over here. And actually, what will be our spectator ion is actually the chlorides, which is the thing not changing, right? The charge is the same on both sides. And really what is happening in this case is the zinc and our 2H pluses going to our zinc and our hydrogen gas. And what's happening here is the zinc is actually laying up a couple of electrons over there to our two hydrogens. The hydrogen is going to gain the electrons. It's actually floating around in the solution, going to gain those electrons and become hydrogen gas and start to bubble out of the solution. So what happens in this case is actually you have these H pluses floating around in the solution. The zinc is going to come into the solution and give away some electrons. Those guys are going to gain those electrons and it'll become hydrogen gas, and you'll start to see a bubble in your test tube and sort of bubble out of solution in that case. So that's really what's happening in this case. Now, let's say we try to do this with something else. Let's just say we tried to do this reaction with copper. So we take copper and we want to do the same reaction with our hydrochloric acid. So now we have our copper coming in to try to replace our hydrochloric acid. Copper is actually lower on the list than hydrogen, which means it's actually less reactive than hydrogen, which means this reaction is not going to take place because copper is less reactive than hydrogen. So that reaction will not take place. The zinc one will in this case. There's also some more specific situations for hydrogen replacements that you can see up here. Sometimes it may take cold water, steam, or acid to do it. Sometimes you need an actual acid for the hydrogen to displace. So are some rules that can happen with that. So not all single replacement reactions will happen. So once again, anything higher in the list should have no problem replacing somebody lower in the list. And again, anybody lower in the list will have some problems. It also, again, for our halogens works the same way. So if we had something like, let's see here, Cl2 plus a little sodium bromide. In this case, 0 plus 1 minus 1. So this guy's going to come in and kick out the chlorine. Chlorine is more reactive than bromine. It's higher on the list. So this should happen. The sodium will now join up with the chlorine, which will become chloride minus 1. The bromine will come out and have no charge, how it naturally comes. We'll do a little balancing, and there we go. This reaction will take place. Now, if you tried to do, say, I2 plus some sodium chloride. In this case, the I2 coming in would try to kick out the chlorine. I2 is lower on the list than chloride, which means it's less reactive. So no reaction would occur in this particular case. So again, that's how we kind of deal with our nonmetals or our halogens in this case. All right, combustion reactions are another type of redox reactions, and they do fall under the redox umbrella. And really the simplest definition of combustion actually is this one. You just need oxygen involved, pretty much. So you just need oxygen in there. And technically speaking, it's a combustion reaction. Most people, when they look at combustion reactions, usually are thinking of the organic combustion, which is what we see here. Something that's organic is typically something that has carbon, hydrogen, or oxygen. And we have O2 and CO2 and water are your products that are typically made. So once again, organic, O2, CO2, and water. So that is a combustion reaction. By the way, saw this earlier. This guy here is technically a combustion reaction because it actually has oxygen. So basic definition of combustion is you just need oxygen there. Most people, if you say combustion reaction, thinks about the organic combustion, like methane there, propane, plus some oxygen makes carbon dioxide and water. Now, a synthesis reaction is another type of redox reaction. So this is a redox reaction. Electrons being transferred, synthesis or combination. Synthesis or combination has a general formula of two things make one thing. So two things make one thing, hence the name combination. That is two things make one thing. Two things make one thing. These are all synthesis and combination reactions. And not surprisingly, as we saw earlier, these are also redox reactions as we are gaining and losing electrons. So electrons being transferred. And same thing here, 0, 0, plus 1, minus 2. In this case, the hydrogen is going from 0 to plus 1. So it's being oxidized. The hydrogen. The oxygen is actually going from 0 to minus 2 here. And it is being reduced. Yeah, so the hydrogen is sending electrons over to the oxygen here to basically make water. So synthesis reaction, it's also a combination reaction, which is sometimes what is referred to. It's a redox reaction. And speaking of multiple ways you classify a reaction, well, we could take a look at this one that we just wrote on a second ago on the previous page. And let's just take a look at this one. So that has oxygen, so can be classified as a combustion reaction. That is definitely a redox reaction, as we talked about, electrons being transferred. And that's also two things make one thing, which means it could also be a synthesis or combination reaction. So this one reaction here, for example, depending on what you're looking at, you could actually classify three different ways: combustion, redox, or synthesis. Which way should you classify it? Whichever way makes the most sense based on what you're looking at that particular time is the right way. They're all technically correct classifications of this reaction, and you could definitely classify the same reaction in multiple ways. Just like, again, here, most people would probably classify this as a synthesis or combination reaction, but some people may classify as a redox reaction. So most of the time, probably the top one, somebody would classify that as a synthesis reaction more so than a combustion or a redox reaction. Sort of the opposite reaction here is a decomposition reaction, and a decomposition reaction is really the opposite of a combination reaction. So in a decomposition reaction, one thing makes two or more things. So combination or synthesis, two make one, put it together. Sort of the opposite of that is a decomposition reaction. One thing breaks apart into several things. And in this case, we have our water. If you run an electrical current over it, going to break it apart into two things. So one thing into two things, very common sort of opposite reaction there. So these are more specific ways we could classify reactions. So just to sort of summarize where we are in these type of reactions is this: the big umbrella of double displacement has more specific classifications of precipitation reaction and acid and base reaction. And again, these are the ones that account for two of the three reasons why a reaction takes place: solid being made or water being made. All other reactions pretty much fall under the big umbrella of redox, which is our electrons being transferred. And under that sort of umbrella, they can be more specifically classified as a synthesis reaction or a combination, a decomposition reaction. Decomposition could also be classified as a single replacement reaction. Also a combustion reaction. So these are the kind of big category reactions, redox or double displacement. And again, more specifically under there, you have your more specific classifications for each of these guys. Once again, only redox involves electrons being transferred, no redox happening in double displacement, which are precipitation or acid-base reactions. And all these reactions pretty much boil down to one of those three things happening. Electrons being transferred are solid and water being made. So as you can see here, again, multiple ways to classify the same reaction. And these are, again, sort of the big classifications and the more specific ones underneath. All right, the last thing we're going to talk about here in this chapter is a little bit about energy and chemical reactions. And I think we touched upon a lot of this energy stuff earlier on. But a heat of reaction sometimes is referred to as the delta H, which is the change in enthalpy, which is the most common sort of heat of a reaction. It's really the quantity of heat that is produced or sort of released in their chemical reaction. Remember, units of energy, kilojoules, kilocalories, calories are joules or common ones. Remember, exothermic reaction releases heat and energy. And when we look at a chemical equation, a lot of times we consider the energy, which is what that number represents, as a product. Remember as well, we talked about something like the delta H, or energy value, is typically a negative value when you're dealing with an exothermic reaction. A endothermic reaction is one where energy is absorbed, and we consider heat or energy to be sort of a reactant in that case. Remember, something like delta H, or an energy value for something that's endothermic, will be more of a positive number. These are some energy diagrams, which I think we talked about in that energy chapter, I believe. And remember that when we look at an energy diagram like this, our reactants are actually lower in energy than our products. This represents an endothermic reaction, which means that energy needs to be kind of put in to do that for our reactants to get to our products. Remember that hill that the reactants have to climb is what is referred to as that activation energy. And that activation energy is the minimum amount of energy that's required for a reaction to take place. By the way, I think I might have mentioned in the energy chapter, but if you take the difference between the energy of the products and the difference between the energy of the reactants, that is basically what delta H, or the change in enthalpy for that reaction, is. And because the products are actually higher in energy, because one way that you calculate delta H is you take the delta H of your products minus the delta H of your reactants. So since the products are higher in energy, this is going to be a larger number than our other reactants. So when you take a larger number minus a smaller number, you're going to get actually a positive number when you do that. And that's why our delta H will be positive in this case. When we look at the opposite of this, which is an exothermic reaction, our reactants are actually higher in energy than our products. So energy has to be given off. You can kind of think about it that way. And that represents an exothermic reaction. Remember, our delta H in this case is going to be a negative value. And this is our activation energy here, right? Our E of A. And that's the minimum amount of energy required for those reactants to get to the product side. And that's going to determine how fast or slow the reaction is, right? It is how high that hill that they have to climb to get to the other side. Once again, if you take the difference between the reactants and the products in terms of their energy, that is your delta H value. And once again, you take your products there minus your reactants, final state minus initial state, if you remember that sort of state function what we talked about. So in this case, our products are actually lower in energy, which means it's going to be a smaller number minus a larger number, and that's going to yield us a negative value for delta H, which is again why delta H is typically negative for an exothermic reaction in this particular case. Now, earlier we talked about as well, a catalyst is sometimes put into an equation, and it speeds up a chemical reaction by finding an alternative pathway for that reaction to take place. So one way that it does that is it finds a more efficient way for that reaction to take place. And the reason why the reaction actually takes place faster is in a catalyzed reaction, for example, I'll make it red. It actually will lower this activation energy. catalyst reaction. A catalyst is present. And what that means is instead of these reactants having to climb all the way up this hill before they could come back down, in the catalyzed reaction, because they find a more efficient pathway, the reactants just got to climb this hill, come back down. And that means that there's going to be a greater proportion of molecules that have enough energy to get over that smaller hill than the larger hill. And the result of that is the rate of the reaction will actually speed up because there's more reactants able to actually get to the other side quicker. Kind of like you, if you had to walk over just a small little hill to get to the other side, or if you got to go all the way up the giant hill, it's going to take it much longer to go up and over the other side. And if everybody was doing that, there would be people who go, never mind, I ain't going to walk the giant mountain. But if the mountain was a nice small little hill or got much lower, you would have a greater amount of people that would go up and over that hill. And that's the same thing that happens here. So a catalyst, because it's able to find a more efficient way for that reaction to take place, and it can be as simple as gas molecules flying around and you put a metal in there and everybody's attracted to the metal. So it allows everybody to be in the same location a lot easier rather than just having to fly around and try to find each other without that metal. Everybody kind of is attracted to a central location, allows for a more efficient way for that reaction to take place. And that's what ultimately will lower that activation energy and speed up the reaction. So energy, again, transfers from hot to cold. And we can actually sort of incorporate energy into our sort of calculations, if you will. So for example, here, what this is saying, when we do this reaction, we basically get off 393 kilojoules of energy given off in this reaction. Remember that earlier on in this chapter, we saw that the numbers that we see in front, the coefficients, can be thought of as the moles. So we basically could say for every 1 mole of carbon, we pretty much get 393 kilojoules of energy out. For every 1 mole of oxygen, combined all that right in there, 1 mole of oxygen, we also get 393 kilojoules of energy out. And for every 1 mole of CO2 produced, we also get 393 kilojoules of energy. So you can actually tie the equation to the products and how much energy is given off. So for example, here, if we were to look at this, in this reaction, when 4 moles of HI are produced, how much energy should be released or absorbed in this case? So take a moment and think about it. I'm going to try to find my calculator. It's been a long one here. We haven't found our calculator. So let's dig it out. Okay, so let's take a look at this one. So what can we get from this equation? Well, we could say for every 1 mole of H2, there are 12.6 kilojoules of energy. For every 1 mole of I2, which is the coefficient, there's 12.6 kilojoules of energy. And for every 2 moles, because the coefficient there is 2 of HI, there is 12.6 kilojoules. So in this case, we're interested in 4 moles of HI. So we could do sort of a dimensional analysis, 4 moles of HI. We could use the HI relationship here with energy and use it as a conversion factor. Just like normal opposites will cancel. So 2 moles of HI on the bottom, 12.6 kilojoules up on top. Moles will cancel. Going to give us 4 times 12.6 divided by 2. Looks like a 25.2 kilojoules of energy. All right, well, that's going to be either this one or this one. Definitely not going to be this one or that one. So now we need to figure out, is it absorbed or is it released? So the equation is going to help us. I see this, and it is a reactant, which means like it is gaining energy or absorbing energy, right? And that is what happens when our energy is on the reactant side. It's endothermic, so it's absorbing energy. Remember, if our energy is on the product side, it's exothermic, releasing energy, which means the winning answer here should be B. It should be 25.2 that has been absorbed. And they do agree, so that's good, I suppose. All right. So that wraps up chapter 8, I think it is. So here in the second half, sorry, went a little bit longer than usual, but we did types of reactions, different ways to classify them. And again, the two big ways, redox and double displacement, which has more specific classifications underneath them. And obviously we talked about endothermic, exothermic here in terms of energy of equations. That should wrap it for chapter 8. Thanks for hanging in there, and we'll see you on the next chapter. Have a good one. Bye-bye.
Hello there, and it's that time of the lecture again. It's time for a chemistry joke. Perhaps today we do a classic chemistry joke. Why are helium, curlium, and barium considered the medical elements? Well, if you can't kill him and you can't heal him, I guess all that's left is to bury him. Classic.